Welcome everyone to our session on our programming for beginners. R is a powerful, open-source programming language and software environment used for statistical computing and data visualization. In this session, we'll cover the fundamentals of R, from installation and setup to data manipulation, analysis, and visualization. R is a versatile tool that can be used for a wide range of applications, from scientific research to business analytics. By the end of this session, you'll have a solid understanding of the basics of R and be equipped to start your own data exploration and analysis projects. R is an open-source programming language designed for statistical computing and data visualization. It provides a wide range of statistical and graphical techniques, making it a powerful tool for data analysis and modeling. R is also a software environment that provides a suite of tools for working with data, including data manipulation, calculation, and graphical display. RStudio is a popular integrated development environment IDE that enhances the R experience. R is a versatile and flexible language that is widely used in academia, research, and industry for its robust data analysis and visualization capabilities. R is an open-source software, which means it's free to use, modify, and distribute. This makes it accessible to a wide range of users. R provides a comprehensive set of statistical and graphical techniques, making it a powerful tool for data analysis, modeling, and inference. The R community has developed thousands of packages that extend R's functionality, allowing users to quickly implement advanced analytics and visualizations. R can be used on Windows, Mac OS, and Linux, making it a versatile choice for data scientists and analysts across different operating systems. R is a powerful programming language that excels at statistical analysis and data visualization. It has a vast library of packages that provide advanced analytics capabilities for data scientists and researchers. Compared to other general-purpose languages like Python and MATLAB, R is specifically designed for working with data. R's syntax is more concise and expressive for tasks like statistical modeling and exploratory data analysis. This makes R a popular choice for those focused on data-driven insights and advanced analytics. RStudio is a powerful integrated development environment IDE for the R programming language. It provides a modern, intuitive coding interface that streamlines the R programming experience. The clean interface, intelligent code editing, and integrated debugging tools help users write and test R code efficiently. RStudio seamlessly integrates with R's powerful data visualization capabilities. Users can create and customize high-quality plots, graphs, and charts directly within the IDE. This allows for immediate data exploration and presentation. RStudio also supports collaboration through features like version control, project management, and sharing capabilities. Users can easily work on projects together, track changes, and share their work with colleagues or the broader R community. R is the primary programming language we'll be using throughout this presentation. It's a powerful and flexible tool for data analysis, visualization, and statistical modeling. To get started with R, you'll need to download and install the latest version from the official R website. The installation process is straightforward and similar across Windows, Mac OS, and Linux platforms. In addition to R, we recommend installing RStudio, a popular integrated development environment IDE that provides a user-friendly interface and additional tools to enhance your R programming experience. RStudio makes it easier to write, test, and debug your R code, as well as manage your projects and access a wide range of packages and libraries. The installation of both R and RStudio should only take a few minutes. Once you have them set up, we'll dive into the basics of using R for data analysis and visualization. The R user interface is a powerful tool for writing, executing, and debugging R code. The code editor provides features like syntax highlighting and code completion to enhance the coding experience. The interactive console allows users to enter R commands, view output, and explore data interactively. The data viewer makes it easy to inspect and understand the structure and contents of data within R. These features of the R user interface help make R a versatile and user-friendly environment for data analysis and programming. R has several fundamental data types that are essential for data analysis and programming. The numeric data type allows for both integer and floating point values, enabling quantitative calculations and analysis. The character data type is used to represent text, strings, and other alphanumeric information. The logical data type stores Boolean values of true and false, which are useful for conditional operations and logical reasoning. R also provides a complex number data type for working with imaginary and complex value data, which can be important in certain scientific and mathematical applications. Variables are an essential part of programming in R, allowing us to store and manipulate data throughout our code. We create variables by using the assignment operator, =, to associate a name with a value. Once defined, we can assign variables different types of data, like numbers, text, or logical values. Variables can be reassigned new values as our program runs, giving us flexibility to work with changing data. Understanding how to properly define and use variables is a fundamental skill for any R programmer. Arithmetic operations are fundamental to working with data in R. We'll cover the 4 basic arithmetic operations: addition, subtraction, multiplication, and division. Addition uses the plus operator to combine numeric values. Subtraction uses the operator to subtract one value from another. Multiplication uses the asterisk operator to multiply numeric values. Division uses the slash operator to divide one value by another. These basic operations allow you to perform calculations and transformations on your data in R. Functions in R are reusable blocks of code that perform a specific task. They allow you to encapsulate logic and parameters for easy reuse. You can define your own custom functions using the function syntax. This lets you package code into a named, parameterized unit. Once defined, you can call functions by name, passing any required arguments. This allows you to execute your packaged code with different inputs. R also provides a wide range of built-in functions for common tasks like data manipulation, statistical analysis, and visualization. Our packages are pre-built tools and algorithms that extend the functionality of the R language. The R community continuously develops and shares new packages, allowing users to leverage the latest advancements in areas like data analysis, visualization, and machine learning. Packages integrate seamlessly with the R ecosystem, making it easy to install, load, and incorporate them into your data workflows. The key steps for installing and managing our packages are finding, installing, versioning, and loading them. Searching the CRN repository and browsing popular package lists can help you discover the right packages for your needs. Use the install.packages function to download and install packages directly within R or RStudio. Regularly update packages to ensure you have the latest stable versions using the update.packages command. Once installed, load packages into your R session using the library function to make their functionality available. Loading packages is an important first step when working in R. To load a package for use in your current R session, you call the library function and pass the package name as an argument. For example, to load the tidyverse package, you would do library tidyverse. You can also automatically load packages at the start of your R session by adding library calls to your .R profile or R startup script. This ensures the packages you need are always available when you start R. Vectors are a fundamental data structure in R, representing a one-dimensional array of elements of the same data type. They can store numbers, characters, or logical values. You can create vectors using the C function, which combines individual elements into a single vector. Vectors can also be generated from other data structures like sequences or repetitions. Vector elements can be accessed using their index, starting from 1. You can use square brackets to select specific elements or ranges within a vector. The C function is the most common way to create a vector in R. You simply pass the individual elements you want in the vector as arguments to C. You can also generate a sequence of numbers using the operator or the seq function. This is useful for creating vectors of equally spaced values. The rep function allows you to repeat scalar values or existing vectors to quickly create new vectors of the desired length. Vectors can be extracted from other data structures like data frames and matrices using indexing or accessor functions. The slide covers different ways to access individual elements of a vector in our programming language. First, we can use indexing to retrieve a specific element by its numeric position, starting at 1. Next, we can select a range of elements using a colon, like getting the second through fifth elements. We can also use logical indexing to choose elements that meet a certain condition, like all positive values. Finally, we can assign named elements to a vector and access them by their names. These techniques provide flexibility in working with vector data and extracting the specific information we need. Vector operations are a fundamental part of working with data in a vectorized way. We'll cover 3 main types of vector operations: arithmetic, logical, and relational. Arithmetic operations like addition, subtraction, multiplication, and division are applied element-wise between corresponding elements in the vectors. Logical operations like and, or, and not allow you to create new logical vectors based on conditions. Relational operations like less than, greater than, and equals compare elements between vectors and return a new vector of logical values. Understanding these vector operations is crucial for efficiently manipulating and analyzing data in a vectorized manner. Matrices are a powerful data structure and are that allow us to work with tabular data in a more structured way. Unlike one-dimensional vectors, matrices organize data into a grid-like format with rows and columns. This grid-like structure enables more advanced data manipulation and analysis compared to simple vectors. For example, we can perform matrix operations like multiplication, inversion, and decomposition that are very useful in data analysis and modeling. Matrices are a fundamental building block for many machine learning and statistical techniques, so understanding how to work with them is an important skill for any data scientist. Matrices are a powerful data structure in R, allowing you to work with two-dimensional arrays of data. The matrix function is used to create matrices, taking a vector of data and organizing it into rows and columns. You can specify the number of rows and columns using the row and col arguments. By default, the data is filled in column-wise, but you can control this behavior. Once you have a matrix, you can access individual elements using row and column indexing, just like with vectors. The slide covers how to access individual elements within a matrix using row and column indices. For example, you can get the element in the second row and third column by using my_matrix 2, 3. You can also retrieve entire rows or columns by omitting one of the indices, my_matrix 4, to get the fourth row, or my_matrix 6 to get the sixth column. Finally, you can use logical vectors to select matrix elements that meet certain conditions, like my_matrix 0, to get only the positive values. Matrix operations are fundamental techniques for working with data in matrix form. We'll cover three key matrix operations: addition/subtraction, multiplication, and transposition. Matrix addition and subtraction allow you to combine or compare data stored in matrices of the same dimensions. Matrix multiplication is a powerful technique for transforming data, like applying linear models or projecting data into new coordinate systems. Matrix transposition interchanges the rows and columns, which is useful for reshaping data between wide and long formats. Data frames are the most commonly used data structure in R. They are two-dimensional tables that store data in a spreadsheet-like format. Rows represent observations, and columns represent variables. Unlike vectors and matrices, data frames can hold different data types in each column. This makes them a versatile choice for working with complex, heterogeneous datasets. Data frames are the fundamental data structure in R, allowing us to work with tabular data. We create data frames by defining the variables columns that will make up the table. Each column can hold a different data type: numeric, character, logical, etc. Once the column structure is set, we add rows of data to populate the data frame. This data can be input manually or imported from external sources like CSV files or databases. It's important to use clear, descriptive names for the columns to make the data frame intuitive and easy to work with. Column names should be unique and follow best practices for variable naming. R will automatically detect and assign the appropriate data type to each column, but we can also manually specify the data type if needed. Data frames are a key data structure in R for working with tabular data. We can access individual elements in a data frame using row and column indices, like df2, 3, to get the element in the second row and third column. To retrieve entire rows or columns, we can omit one of the indices. df4 gets the fourth row, and df6 gets the sixth column. Using the $operator is a more readable way to access columns by their names, like df$h. We can also apply logical conditions to select rows or columns that meet certain criteria, like df$gender equals female, to get all rows for female participants. Data frames are a fundamental data structure in data analysis, allowing you to store and manipulate tabular data. Today we'll cover 4 key operations you can perform on data frames: subsetting, filtering, sorting, and transforming. Subsetting lets you select specific rows and columns from a data frame, extracting just the data you need for your analysis. Filtering allows you to include only the rows that meet certain criteria, like all customers from a specific region. Sorting reorders the rows based on the values in one or more columns, making it easy to identify top performers or other patterns. Transforming modifies the values, types, or structure of data frame columns, preparing the data for further analysis. These data frame operations form the building blocks for working with tabular data and getting insights from your information. Lists are versatile data structures that can hold elements of different data types, including vectors, matrices, and even other lists. They provide a way to organize complex, heterogeneous data. Unlike vectors and data frames, lists are not restricted to a single data type per column. This allows lists to store a wide variety of information in a single object. You can create a new list using the list function and passing the elements you want to include, which can be of any data type. The slide introduces the topic of creating lists in programming. It highlights two key ways to create lists. Using the list function to directly specify the elements to include. Combining existing data structures like vectors and data frames into a single list. Lists are a flexible data structure that can hold a mix of data types, making them useful for organizing complex information. The list function allows you to easily create a new list by passing in the elements you want to include. Combining existing data structures into a list is a powerful way to group related data together for easier management and analysis. List elements can be accessed in several ways. Indexing. Use numeric indices to retrieve specific elements, starting from 1. Named access. If the list has named elements, use the $operator or double brackets to access them directly by name. Subset with brackets. Use square brackets to extract a subset of a list, either by index or by name. Unpack elements. Assign individual list elements to new variables using the operator to easily work with specific components. Lists are a powerful data structure and are that allow you to store and work with complex, heterogeneous data. Today we'll cover 3 key list operations: subsetting, modifying, and applying functions. Subsetting lets you access individual elements of a list, either by numeric position or named components. This is useful for extracting specific parts of a complex list structure. Modifying lists allows you to add, remove, or update elements as needed for your analysis. Lists provide a flexible way to reorganize and transform your data. Applying functions to lists enables powerful data transformations and aggregations, even on complex, mixed-type data. We'll explore examples of each of these list operations in the upcoming slides. Conditional execution is a key concept in programming that allows your code to make decisions and take different actions based on the state of your data. The basic if-else structure is the foundation of conditional execution. It evaluates an expression and executes one block of code if the condition is true, and another block if it's false. You can build on this by chaining multiple if-else statements together to handle more complex scenarios with multiple possible outcomes. One powerful aspect of if-else in R is that it can operate on entire vectors, applying the conditional logic element-wise. This makes it very efficient for data manipulation tasks. Understanding how to effectively use if-else statements is an important skill for any R programmer. They provide the flexibility to create dynamic, responsive programs that can adapt to different situations. For loops in R provide a way to repeatedly execute a block of code a specified number of times. The loop iterates through a sequence of values, allowing you to perform an action on each element. The basic syntax is: for variable in sequence, a hashtag code to execute. For loops are useful when you know in advance how many times you need to repeat an operation, such as processing each element in a vector or data frame. For loops are often preferred over while loops when the number of iterations is known upfront. For loops offer several benefits compared to other control structures, including a clear and predictable flow of execution and better performance when the number of iterations is fixed. While loops in R allow for dynamic, open-ended repetition of a block of code, unlike the fixed iterations of for loops. The loop continues as long as the condition expression evaluates to true, and terminates once the condition becomes false. This flexibility makes while loops useful for processing data with unknown or variable lengths. However, while loops require careful consideration to avoid infinite loops or other unintended behavior, ensure the loop condition will eventually become false. The if-else function in R provides a concise way to implement if-else conditional logic in a single line of code. This makes it a powerful tool for streamlining decision-making in your programs. Unlike basic if-else statements, ifelse can operate on entire vectors, applying the conditional logic element-wise. This allows for efficient, concise data manipulation across large datasets. The ifelse function takes 3 arguments: a logical test, a value to return if true, and a value to return if false. This flexible structure enables you to handle both positive and negative cases with a single function call. You can chain multiple ifelse calls together to create more complex conditional logic, allowing for sophisticated decision-making within your code. The apply function allows you to easily apply a function to the rows or columns of a matrix or data frame, making it easier to work with and analyze your data. Laply takes a function and applies it to each element of a list, returning a new list with the results. This is a powerful tool for working with lists of different data types. Saply is similar to Laply, but it tries to simplify the output, returning a vector or matrix when possible. This makes it a convenient choice for many data manipulation tasks. These 3 functions, apply, Laply, and Saply, provide flexible and efficient ways to perform operations on your data in R. The slide introduces the topic of importing data from CSV files in R. CSV files are a common format for tabular data, such as spreadsheets, that can be easily imported into R for analysis. R provides built-in functions like read.csv to read CSV files directly into data frames, which are the primary data structure in R. When using read.csv, you need to specify the file path or URL of the CSV file you want to import. The function also offers various arguments to customize the import process, such as selecting specific columns, handling missing values, and specifying the delimiter used in the CSV file. Importing data from CSV files is a fundamental task in R, as it allows you to bring in data from various sources for further analysis and manipulation. Excel data is easily accessible in R using packages like readexcel. The read_excel function allows you to directly read .xls and .xlsx files into data frames. Provide the file path or URL of the Excel workbook you want to import. R will automatically detect the sheet structure and data types. The read_excel function offers customization options. Select specific sheets to import. Handle missing values. Control data types. This streamlines the process of bringing spreadsheet data into your R environment for analysis. Database integration in R is a powerful feature that allows you to seamlessly connect to a variety of database systems and import data directly into your analysis workflows. Popular packages like dplyr, RMySQL, and RSQLite provide intuitive interfaces for establishing secure connections to databases and executing SQL queries within your R code. This level of database integration gives you tremendous flexibility and control over your data. You can extract, transform, and combine data from multiple sources, creating a centralized hub for your data-driven projects. With these capabilities, you can build robust, data-centric applications that leverage the full power of your database resources. Data cleaning and manipulation is a crucial step in the data analysis process, ensuring the integrity and reliability of your results. We'll start by identifying any issues in the data, such as missing values, outliers, or inconsistencies that could skew our analysis. Using functions like summary and str will help us understand the structure of the data and pinpoint areas needing attention. Next, we'll cover handling missing data. Depending on the nature of the data and the use case, we can replace or impute missing values using techniques like mean/median imputation or k-nearest neighbors. We'll also discuss data transformations, operations like filtering, sorting, merging, and reshaping the data to prepare it for analysis. Leveraging functions from packages like dplyr and titer can streamline this data wrangling process. Finally, we'll touch on data validation, checking for duplicates, enforcing data types, and ensuring consistency across related variables. This helps guarantee the reliability and integrity of our analyses. This slide provides an overview of 4 key data visualization techniques we'll be exploring in more depth. Scatterplots allow us to visualize relationships between numeric variables, uncovering patterns and trends in the data. Bar charts are useful for summarizing and comparing categorical data, helping us identify key insights. Histograms enable us to explore the distribution of a numeric variable, understanding its spread and shape. Box plots visualize the distribution and outliers of a numeric variable, allowing us to identify unusual data points. These 4 visualization types will be the focus of our discussion as we learn to effectively explore and analyze our data. Descriptive statistics provide important summary measures to understand the central tendency and spread of a dataset. Key measures include the mean, median, and standard deviation. These summary statistics give us a high-level view of the data and help identify patterns and trends. In addition to numerical summaries, data visualizations like histograms, box plots, and scatter plots are powerful tools for exploring the underlying distribution and relationships in the data. Descriptive statistics lay the groundwork for deeper statistical analysis by helping us identify trends, outliers, and connections between variables. Understanding the basic characteristics of the data is a critical first step before moving on to more advanced analytical techniques. Hypothesis testing is a statistical method for evaluating whether a particular claim or hypothesis about a population parameter is likely to be true. We start by defining a null hypothesis, H0, and an alternative hypothesis, H1, that describe the relationship or difference we want to test. Next, we collect relevant data from a sample that will provide evidence to support or refute the hypotheses. We then use statistical methods to compute a test statistic that quantifies the difference between the observed data and the null hypothesis. We compare the test statistic to the expected distribution under the null hypothesis to find the probability, or p-value, of obtaining the observed result. If the p-value is less than the chosen significance level, we can reject the null hypothesis and accept the alternative hypothesis. This allows us to draw a conclusion about the population parameter based on the sample data. Linear regression is a powerful statistical technique that helps us understand the relationship between variables. It allows us to model a linear relationship between a dependent variable and one or more independent variables. The key characteristic is that it finds the line of best fit that minimizes the sum of squared differences between the observed and predicted values. Linear regression has many practical applications, such as prediction, forecasting, and understanding how different factors influence an outcome. This technique is widely used across various fields, from economics and finance to marketing and engineering. Logistic regression is a powerful statistical technique for modeling binary outcomes, like whether a customer will purchase a product or not. The model uses a sigmoid function to transform the linear combination of predictor variables into a probability between 0 and 1. By setting a threshold on the predicted probability, we can classify observations into one of 2 categories based on the learned decision boundary. Logistic regression estimates the model parameters using maximum likelihood estimation, which finds the coefficients that maximize the probability of the observed data. This technique is widely used in fields like marketing, healthcare, and finance for tasks like customer churn prediction, disease diagnosis, and credit risk assessment. Time series analysis is a powerful statistical technique that allows us to examine data points collected over time. This enables us to identify trends, patterns, and relationships in the data, which can be incredibly valuable for forecasting, understanding seasonality, and making data-driven decisions. The key characteristic of time series data is that it has a natural ordering based on time, which allows us to analyze the temporal relationships between variables. Time series analysis is widely applied in domains like finance, economics, and marketing to forecast stock prices, model inflation, and analyze sales trends. Common modeling techniques include autoregressive AR, moving average, MA, and ARIMA models, which provide a framework for capturing the underlying structure and dependencies in time-ordered data. Clustering is an unsupervised machine learning technique that groups similar data points together, allowing you to discover natural structures and patterns within your data. The core idea of clustering is to identify groups of data points that are more similar to each other than to points in other groups, based on their features or characteristics. Clustering algorithms iteratively assign data points to clusters, minimizing the distance between points within a cluster and maximizing the distance between clusters. This reveals inherent structure in the data. Popular clustering algorithms include k-means, hierarchical clustering, Discan, and Gaussian mixture models, each with their own strengths and applications. Clustering has numerous applications, such as customer segmentation, anomaly detection, image segmentation, and biological data analysis, enabling deeper insights and more targeted decision-making. We've covered the core fundamentals of R, a powerful, open-source programming language for data analysis and visualization. R has an extensive ecosystem of packages that allow you to extend its capabilities to meet your specific needs. Be sure to explore this rich library of tools. To continue growing your R skills, take advantage of the many online tutorials, documentation, and communities available. There's always more to learn. The best way to solidify your R knowledge is to apply what you've learned to your own data projects. Hands-on practice is key to developing real-world expertise. Remember, R is a versatile tool that can be tailored to your unique analytical requirements. Keep exploring and don't be afraid to experiment. We hope you find the video useful. See you in our next one.